Hello, I'm Manoj Puravankara. I work at the Department of Astronomy and Astrophysics at the Tata Institute of Fundamental Research in Mumbai. Today's lecture is on star formation. We will discuss how stars are formed out of interstellar matter, the material between stars in our galaxy, and how star formation processes give rise to protoplanetary disks, which are the building blocks of planetary systems. So let's start by asking the question, how do we know stars are currently being formed in our galaxy? So we know that the star formation happened when our galaxy formed, but are stars forming now in our galaxy? The answer to this question is, our galaxy is greater than 13 giga-year old, and stars have finite lifetimes. For example, the lifetime of sun-like stars are much shorter, less than 9 giga-years or so. So if stars were not born, we would not be seeing such stars in the night sky. So star formation is currently happening in our galaxy. If that is so, where are stars born? Stars are born in the dense and cold interiors of molecular clouds in our galaxy. Young stars are always seen associated with the molecular clouds. So let's look at the molecular clouds, the sites of star formation in our galaxy. So as I said, stars are formed out of interstellar matter. So the material between the stars are called interstellar medium. Interstellar medium is typically about 10% of the total stellar mass content of the galaxy. The interstellar medium consists of both gas and dust. It's 99% gas and 1% dust by mass. Most of the gas is in the form of atomic hydrogen, about 60% of it, and about 20% is in the form of molecular hydrogen. Image below shows the distribution of interstellar gas and dust in our galaxy. As you can see, the top panel is atomic distribution of atomic hydrogen, and the one below it is distribution of molecular hydrogen, and the dust distribution is the panel below it. So what I want you to notice is that the dust distribution and the molecular gas distribution are spatially coincident. So molecular hydrogen clouds are the birthplace of stars, and they are also the largest gravitationally bound structures in the galaxy. So these cloud complexes have masses of the order of 10 to the 4, 10 to the 5 solar masses and sizes of several tens of parsecs. Parsec is a unit astronomers use to measure distance. It's about 3.3 light years. On the left panel, I show an image of a molecular cloud. This particular one is of Eagle Nebula in Orion. This is a color composite of infrared emission at 70 microns, 160 microns, and 250 microns. So this is made of, at these wavelengths, it's a dust that is emitting cold dust with temperatures of few tenths of Kelvin. So what you can see here is, although we are tracing the dust, we are also, since dust and molecular clouds spatially coexist, so we've traced the structure of molecular clouds here. So you can see here the stars that are being formed. The redder regions are cooler regions where stars are actually being formed, and the bluer regions are slightly warmer regions which is reflecting, scattering the light from the newborn stars. Molecular clouds are often filamentary and clumpy, as you can see from this figure. So they are also cold with temperatures of few tenths of Kelvin, and dense with density ranging anywhere from 100 to 10 to the 5 particle per cc. Stars are often formed in clusters. Here I show two such examples. The one on the left is NGC 2264. This is a cloud in the Monoceros region. You can see here the stars forming in several hundreds of stars forming together. The red point sources that you see here are stars in this cluster. And on the right, what we have is the Orion Nebula cluster, and here again you have thousands of stars being formed as part of this cluster. So if stars are formed in clusters, what is the distribution of mass of the stars that are being formed? So this is often referred to as the initial mass function. Empirically and observationally, we find that the initial mass function or the number of stars within a given mass range given as dn by dm follows a power law with mass, stellar mass to the power minus alpha, where alpha is 2.34 stellar masses greater than 0.5 solar mass. So what this means is that when stars are formed in clusters, there are many more low mass stars formed than the high mass stars. So the IMF, or the initial mass function, is bottom heavy. So although stars are formed in clusters, and let us now, to appreciate the physics of star formation, let us look at the formation of single stars. This cartoon here captures our current understanding of how stars form. The various evolutionary stages that star formation process go through are depicted here. So the first phase, the process begins when a slowly rotating molecular cloud core collapses under its own gravity to form a central protostar, a disk around it, and an overlying envelope from which the material is raining down onto the disk. At some time during this phase, a bipolar outflow breaks out along the polar axis of the system. We don't entirely understand how these outflows are launched. Eventually, the envelope envelope is dissipated away either by draining onto the disk or by the action of the outflow, cleared by the outflow or jet. And what we are left with is a central young star, which we now call a pre-main sequence star, surrounded by a disk. So these disks are known as protoplanetary disks. These are the birthplace of planetary systems. Eventually, the disk also dissipates by forming planets, and you are left with a young star with a planetary system around it. So this is the sequence which we believe the star formation process go through. So let's now look at each of the stages in more detail. The first is the gravitational collapse of the molecular dense core and the formation of protostars. To illustrate ideas, let us first consider an isothermal cloud of temperature T and of uniform density, molecular density NH2. Here we are only considering thermal pressure to support the cloud against gravity. And the thermal pressure is directly proportional to the density and the temperature of the cloud. Now, if this is the case, there is a minimum radius and mass beyond which the cloud will collapse. The gravity will overwhelm the thermal support for the cloud, and the cloud will collapse. So this minimum length and mass is often called Jeans length or Jeans mass, after James Jeans, who was an English physicist and astronomer who worked this out for the first time. So here I have given the expression for Jeans length or size for typical values of temperature and density, molecular density. And you can see that for 10K and a molecular hydrogen density of about 10 to the 4 particle per cc, it works out to be around 0.1 parsec. Whereas Jeans mass for the same parameters of same values of T and density works out to be about 1 solar mass. So this is the typical size and mass of the cloud dense core that will collapse to form stars, low mass stars. So once the gravity overwhelms the supporting thermal pressure, the whole entire cloud collapses, and the free fall time then is given by this. It's 3 pi by 32 g rho, where capital G is the gravitational constant and rho is the mass density. So as you can see, the free fall time depends only on the density, it goes as the inverse of the square root of density. And numerically, it's about, for the typical densities of 10 to the 4th particle per cc, it's about 0.5 million years. It's very short. So as I said, the thing to notice is that free fall time depends only on density and not on radius, which means that material from all radii will arrive at the center simultaneously, which would then imply that the outermost radii must fall in the fastest, or this collapse. In other words, this collapse would look like an outside-in collapse. And as a corollary, the mass infall rate would be largest for outer parts of the cloud. Now, more realistically, even if you start with a constant density isothermal cloud, there is bound to be central condensation. The density eventually will take the form of 1 by r square or so. If we have such a cloud, which is often referred to as singular isothermal cloud, where the density goes as 1 by r square, then the collapse time or the free fall time will scale with r, or the radius of the cloud. So what this means is that for outer parts of the cloud, the collapse time is longest, and for inner parts of the cloud, the collapse time is shortest. So this would result in what is known as an inside-out collapse. The innermost regions will collapse first, the outer parts will take longer to fall in, or in other words, the mass within a radius r will grow linearly with time. An implication of this is that infall rate would be constant and is given numerically by this value, cube of the Cs cube by g, where Cs is the sound speed. And for the typical values of the dense core, it's about 10 to the minus 6 solar mass per year. So dense cores that collapses, they also have some initial rotation. So one thing to keep in mind here is that the specific angular momentum goes as omega r square, where r is the radius of the cloud. So the initial dense core typically has a size of 0.1 parsec, as we have seen from the gene's length, and that's about 10 to the 15 meters. And this has to collapse to form a star of 10 to the 9 meters, radius 10 to the 9 meters. So you can see this as, since the angular momentum goes as r square, so there's 12 orders of magnitude in angular momentum has to be shed. So this is always not possible, and as a result, when a rotating dense core collapses, it doesn't collapse onto a central point or a central body. Instead, it forms a flattened geometry, which we call disk, which is shown in the left panel here. So the disk size, the disk that is formed, will have a centrifugal radius, which will increase with time as t cube. So as the collapse proceeds, the disk radius increases rapidly with time. One can also recast the centrifugal radius of the disk during the initial collapse as a function of mass in the central body, in the central object, and it goes as m cube. Numerically, it can be written this way. So what this means is that very low mass stars will have negligible initial disk, but for when the mass increases, so most of the material must first collapse into a disk before it can be accreted onto the star. So most of the material that goes on to build the star must be processed through the disk. This is an important implication for both star and planet formation. Here are some of the interesting questions or open questions regarding the protostellar collapse. So during the protostellar phase, one could characterize the protostellar phase through three mass flows: the envelope infall, the disk accretion, and the outflow. So if you can ideally measure these three mass flow rates, one would have characterized the protostellar evolutionary phase, but this is often not easy. So some of the open questions in this area are how well are the envelope infall rate and the disk accretion rate coupled, and how efficient are disks in transporting mass. It turns out that disk is not a very efficient in transporting mass. So that is what is providing the bottleneck in building the star. So the other question of interest is, do more massive protostars accrete at a higher rate than low mass protostars? So many of these are open questions even today. So in the protostellar collapse case, evolutionary phase, let me just highlight one particular problem which people have been trying to grapple with, and that has to do with the protostellar luminosity or the protostellar accretion rate. So if you take the total power output of a protostar as a measure of its accretion rate, so typically the power output from the protostar is the sum of the photospheric emission plus the luminosity or power output due to accretion. The accretion luminosity is given by some efficiency factor times gm star, or the mass in the central object, which is a function of time, times m dot, the accretion rate, the disk accretion rate, divided by r. So to form a 0.25 solar mass object, you need to accrete at around 2 times 10 to the minus 6 solar mass per year. Now, for typical values, if the accretion rate onto the protostar is of the order of 10 to the minus 6, the accretion luminosity should be of the order of 10 solar luminosity. However, if you look at this figure here on the y-axis, which is bolometric luminosity, you can see that there are very few stars with bolometric luminosities above 10 solar luminosities. Most of the stars have luminosities below it. And this is only for a 0.25 solar mass star. So what I am trying to say is that most of the observed L-bol or the bolometric luminosities, or the total power output from the protostars, are significantly less than 10 solar luminosities. What this means is that the accretion rates inferred from the measured bolometric luminosity of the protostars are significantly lower than that required to form a star within the protostellar lifetime. So then how do stars form? So the one way out of this conundrum is if disk accretion is episodic. So the way it works is, for most of the time the accretion rate is at a very low level, and most of the stellar mass is built during this major accretion outburst events, and such outbursts have been observed in protostars. So this has an important implications for protoplanetary disks and planet formation. It is that the details of the disk accretion, the outbursts, etc., sets the initial conditions for planet formation in protoplanetary disks. Such huge accretion outbursts can actually erase the physical and chemical signatures of the disk, history of the disk. Now let us move on to pre-main sequence stars and the protoplanetary disks. So this is this particular evolutionary stage. Once the envelope has been dissipated either by draining onto the disk or blown away by the outflow or the wind, one is left with the pre-main sequence stars and a protoplanetary disk. So then we say the star has entered its pre-main sequence phase. So they contract along these evolutionary tracks towards the main sequence. One important point about pre-main sequence evolution is that hydrogen burning, nuclear fusion hasn't started in the stellar cores. The primary source of luminosity during the pre-main sequence evolution of a star is derived from gravitational contraction. So these stars are contracting along the evolutionary tracks. So part of that energy is released as radiation, radiated away. So these pre-main sequence stars are surrounded by accretion disks. So they are accreting at a relatively low rate, 10 to the minus 8 solar mass per year or so for low mass stars. So how do we know they are surrounded by disks? Protoplanetary disks have now been imaged both in scattered light, as is shown here. So this is an image of a disk using a coronagraph. The central star has been blocked, and the black area here is because the central star has been blocked by the coronagraph, and you see the disk in scattered light at 1.8 microns. This is an HST Hubble Space Telescope image. And on the right, this is another coronagraph image. The central star has been blocked out, and you can see the image in scattered light at 1.6 micron. So disks are real, and they do exist around pre-main sequence stars. Disks can also be imaged in thermal emission, by which I mean disks are the disk at various radius are at a certain temperature, and what you see here is an Atacama large millimeter array image, 1.3 millimeter continuum image of a disk around a star called HL tau. So what you see here is the disk emission, the dust in the disk emitting at 1.3 millimeter as a black body. So if disks indeed are heated up and are at various parts of the disk at various radius are at different temperatures, what is the heating source of the disk? Let us examine this question. So disks are for optically thick disks. So what do I mean when I say disks are optically thick disks? What I mean is every annulus of the disk is emitting at its characteristic temperature, like a black body at its characteristic temperature. If that is the case, what is heating the disk? If the accretion in the disk is heating up the disk, then the disk surface temperature is given by Gm star m dot by 8 pi sigma r cube to the power 1 by 4. Here sigma is the Stefan-Boltzmann constant, m dot is the accretion rate, m star is the stellar mass, and r is the radial distance from the star to the disk. But if the heating is due to stellar irradiation, then the disk temperature is given by L star r star by 4 pi sigma r cube. Both, as you can see, both have very similar radial dependence, disk radial dependence. So you can't really distinguish from the temperature profile alone whether the disk is heated by accretion or irradiation. For young pre-main sequence stars, L star is significantly higher than G m star m dot by 2 r star. So that primary mode of disk heating is disk irradiation. The central star heats up the disk for young stars. So let us discuss disk geometry now. Protoplanetary disks are flared. What do I mean by this? The ratio of the scale height of the disk to that of the radius increases with radius. The aspect ratio of the disk h by r, where h is the scale height and r is the disk radius, is given by Cs by omega, where Cs is the isothermal sound speed and omega is the Keplerian angular velocity. For optically thick disks, the temperature profile, as we have seen, goes as r to the power minus 3 by 4, which then gives the aspect ratio scaling as r to the power 1 by 8. If the disk is optically thin, then the temperature profile is r to the power minus 1 by 2, and then the aspect ratio is scales as r to the power 1 by 4. So in both cases, the disk aspect ratio increases with disk radius, or in other words, we say disks are flared. So the shape of the disk is something like this. When you go to longer radius in the disk, the scale height increases. So disk has a bowl shape. How about the disk lifetimes? What is shown here is the disk frequency of a star cluster. So what this means is what is plotted on the y-axis as disk frequency is the number of stars with disks divided by the total number of stars in that young cluster as a function of the cluster age. You can clearly see that at very young age, up to 80 to 90% of the cluster members have disks. But by about 3 to 5 million years, 90% of the stars have lost their disks. So it would appear that most disks dissipate in about 3 to 5 million years. Now, this has important implications for planet formation. What this means is that a Jupiter-like gas giant planet will have to be formed within 3 to 5 million years because otherwise, before the disk is dissipated. So, this has prompted many of the theoreticians to come up with a faster mechanism for the formation of Jupiter-like planets. So, how do we know protoplanetary disks are indeed the birthplace of planets? Do we have evidence for planet formation in this? We now have actually have imaged protoplanets that are being formed or in the formation of in the process of forming in the disk. So, when a Jupiter-like planets is being formed in a disk, it opens up gaps within the disk, which is imaged in this particular star PDS-70. This is a 5 million year old star. This is again a coronagraphic image. The central starlight has been blocked out, and you can see the disk in scattered light. This is at 2.2 micron, and you can also see the new planetary object which is being formed here. And look at the right panel. This is a thermal emission at 1.3 millimeter from a disk. You can see the ring structure. There are gaps within the disk. These are thought to be formed by Jupiter mass planets that are created by Jupiter mass planets that are being formed in this disk. So, we now have evidence for planetary mass object carving out gaps and cavities within the disk. So, here I show images of about 15 disks, 20 disks or so obtained as part of the D-SHARP project with the Atacama Large Millimeter Array. Although not all substructures that you see are caused by planets, a good fraction of them are indeed gaps opened up by Jupiter or more massive planets that are being formed in this disk. So, it is clear that protoplanetary disks, which are formed as a byproduct of the star formation process, are indeed the birthplaces of planetary systems. We now have evidence that planetary mass bodies are formed in these disks.